Hello, welcome back once again. Today we have another interesting improper integral. Today we're going to integrate from 0 to infinity 1 over this cubic expression x cubed plus x squared plus x plus 1 dx. Right? Okay, so how do we approach this problem? First, let's make the following substitution. So we're going to let x equals 1 over y. Here, y is a dummy variable, right? So which means that f of x is also equal to f of y. You get the idea? Okay, now, if x is equal to 1 over y, this also implies that y is equal to 1 over x, right? Now, let's differentiate both sides. So we're going to have dx is equal to negative 1 over y squared dy. Okay, so the integral I is going to be equal to the integral. Now let's check out the limits. Now you know from here, when x is approaching 0, y is approaching 1 all over 0, which is infinity, right? And when x is approaching infinity, y is approaching 1 over infinity, which is equal to 0. And here we have 1 all over, so x cubed will be 1 over y cubed, plus x squared will be 1 over y squared, plus x will be 1 over y, and here we have plus 1. Therefore, we're multiplying by dx, which is negative 1 over y squared and dy, right? Okay, now at this denominator, we can make a common denominator there as well, right? So you know what I mean? But before that, let's switch this limit from 0 to infinity, and by so doing there will be no negative sign right over here. So we're going to have this as 1 all over, so this will be y cubed plus y squared plus y plus 1, and then divided by y cubed. So if you split this denominator, you will still get this here back. You get the idea? Okay. So here we're going to have multiply by, this will become dy over y squared. Now, you know, we're taking the reciprocal of, what is that? Y cubed plus y squared plus y plus 1 all over y cubed. So that is going to flip. So the fraction will flip as y cubed, right? Then divided by y cubed plus y squared plus y plus 1, and here we have dy divided by y squared. So we know this will cancel this and leaving us with only y. So we now have our I is now equal to the integral from 0 to infinity. Then we have y divided by y cubed plus y squared plus y plus 1, and then we have dy. Are we making any progress, or are we making the whole thing more complicated? The answer is progress, right? You know I. Now I is equal to, from the original integral, the integral from 0 to infinity, 1 all over y cubed plus y squared plus y plus 1, and then dy, right? That is x actually, right? Okay, so sorry for that. It is x, not y. And this one right over here, remember it is a dummy variable, right? So we're going to change everything to x. So this is going to be x, then divided by x cubed plus x squared plus x plus 1, and then we have dx, right? And from the original integral, we have 1 over x cubed plus x squared plus x plus 1, and then we have dx. Now what happens when we sum these two integrals? So it will be I plus I will be equal to the integral from 0 to infinity. So we have x divided by x cubed plus x squared plus x plus 1 dx, and then plus the integral from 0 to infinity, 1 over x cubed plus x squared plus x plus 1, and then we have dx, right? Okay, so at the left hand side now we're left with 2i right? So this will be equal to, so this will be integral from 0 to infinity. Remember, we have the same denominator, so we can add the numerators x plus 1 and then divided by x cubed plus x squared plus x plus 1, and then we have our dx. But how does this really help us? Well, the denominator here can be factored, right? So this is the trick. Remember, we have x cubed plus x squared plus x plus 1. So I can write this as x cubed plus 1, right? Put this in bracket, and then we have the other one, x squared plus x. So right over here, I will use the sum of two cubes formula. So that is going to, oh, I need to explain this properly. So let us take note. We have a cubed plus b cubed. So this is equal to a plus b multiplied by a squared minus ab plus b squared. So, but how am I going to use that here? Actually, we have x cubed, and this one is same as 1 cubed. So that is going to give us x plus 1 into bracket x squared minus x plus 1. And here we have to factor out x, and we have x plus 1. So you can see x plus 1 is common, so we can take it out, right? So if you take it out here, then we are left with x squared minus x plus 1 and then plus x, which finally give us x plus 1 and x squared plus 1. My God, this is really cool. So we have 2I is equal to the integral from 0 to infinity. So we have x plus 1 divided by x plus 1 multiplied by x squared plus 1, and then we have our dx. Okay, so from here we have some nice cancellations. This cancels this, so we have 2I is equal to, so write this as integral from 0 to infinity, then 1 over, this will be x squared plus same as 1 squared, and then we have the x. So from here we're going to use the standard integral formula. And what's that? The integral of 1 over x squared plus a squared dx is equal to 1 over a, the arctangent or inverse tangent of x divided by a, and then plus c. So use that, we get 2I will be equal to, so 1 over 1 is 1, then the inverse tangent of x over 1, which is same as x, from 0 to infinity. And putting the limits, we get the inverse tangent of infinity minus the inverse tangent of 0. So from here we get 2I is equal to inverse tangent of infinity will give us pi over 2 minus the 0 there, so we get here pi over 2. So finally 2I is equal to pi over 2. So divide both sides by 2, so we get I is equal to pi by 2 divided by 2, which will give us pi all over 4. Oh my God, this is really cool. So this is our solution. So you can see that the integral from 0 to infinity of 1 over x cubed plus x squared plus x plus 1 dx is giving us something really cool and nice. Pi all over 4. If you really enjoy my videos on this channel, kindly support this channel by giving me a subscription. Please subscribe, also like, comment and share.